Good morning everyone. Myself Muskan from BSc Chemistry Honors first year. Today I read a chapter of Physical Chemistry by Dr. S.C. Khetrapal named Electrochemistry. Electrolytic and metallic conduction and factor affecting them. Electrolytic and metallic conduction. Substances which allow electricity to pass through them are known as conductors, whereas substances which do not allow electricity to pass through are known as insulators. Conductors are divided into two classes. Number 1, those which conduct electricity which underlying any decomposition. These are called electronic conductors. Example, metals, graphite and certain minerals. As the name indicates, the conduction in this case is due to the flow of electrons. Number 2, those which undergo decomposition when current is passed through their aqueous solution or melt. These are known as electrolytic conductors or electrolytes. Example, solution of acid, bases and salt in water, fused salt, etc. In this case, the flow of electricity is due to the movement of ions. Electrolytes are further classified into two main categories as strong electrolytes and weak electrolytes. Strong electrolytes are substances like strong acid, example HCl, HNO3, H2SO4, etc. Strong bases, example NaOH and KOH, etc. And most of the inorganic salt, these dissociate almost completely in the aqueous solution and KOH, etc. Aqueous solution or molten state and hence conduct electricity to a large extent. Weak electrolyte can substance like weak acids, example CH3COOH, HCNH2, CO3, H3PO4, etc. And weak bases, example NH4OH, CaOH का whole twice, AlOH whole thrice, etc. These have low degree of dissociation and hence conduct electricity to a small extent. Substances like sugar, urea, etc., the solution of which do not conduct electricity are known as non-electrolytes. Factors affecting electrolytic conduction. The conduction of the solution of an electrolyte depend upon the following factors. Number 1, interionic attraction, which depend upon the interaction between the ions of solute and hence are called solute-solute interaction. On this basis, the substances are classified as strong electrolytes and weak electrolytes as already mentioned. Number 2, solvation of ions, which depend upon the solvation interaction between the ions and the solute and the molecule of the solvent and hence are called solute-solvent interaction. Strong electrolytes are almost 100% ionized in the aqueous solution, whereas weak electrolytes are less than 10% ionized in the solution. However, these are many electrolytes whose behavior is intermediate between strong and weak electrolytes. That is, the dissociation is less than 100% but greater than 10%, and similarly between strong and weak Similarly, their conductance is less than of strong electrolyte but greater than that of weak electrolytes. Such electrolytes are called moderate or intermediate electrolytes. Orthochlorobenzene acid, orthonitrobenzoic acid. Number 3, viscosity of the solution, which depend upon the solvent-solvent interaction. The effect of the all factors decreasing with increasing of temperature. Hence, the electrolytic conduction increase with increase of temperature. On the other hand, the electrical conduction of the electronic conductors decrease with increase of temperature. Alternatively, the factors on which the electrolytic conduction depend are as follows. Number 1, nature of the electrolyte. Strong electrolyte ionize almost completely in the solution and hence conduct electricity to a large extent, whereas weak electrolyte ionize to a small extent and hence conduct electricity to a small extent. Number 2, nature of the solvent. Electrolytes ionize more in a polar solvent, hence greater in the polarity of the solvent, greater is the ionization and hence greater is the conduction. Number 3, concentration of the solution. Higher the concentration of solution, less is the conduction. This is because in a weak electrolyte the ionization is less, whereas in a strong electrolyte the interionic attraction are high at higher concentration. With the dilution, interionic attraction decrease and hence conduction increase temperature. Number 4, on increasing the temperature the dissociation increase and hence conduction increase. Difference between metallic conduction and electrolytic conductors. Metallic conductors. Number 1, flow of electricity take place without the decomposition of the substance. Electrolytic conduction. Number 1, flow of electricity take place accompanied by the decomposition of the substance. Number 2, metallic conductors. Flow of electricity is due to the flow of electrons only, there is no flow of matter. Number 2, electrolytic conductors. Flow of electricity is due to the movement of ions and hence there is a flow of matter. Metallic conductors. Number 3, the electrical conduction decrease with increase of temperature. This is because kernels start vibrating, which produce hindrance in the flow of electron. Electrolytic conductors number 3. The electrical conduction increase with increase of temperature. This is generally due to increase in dissociation or decrease in the interionic attraction. Metallic conductors number 4. The resistance offered by metals is also due to the vibrating kernels. Electrolytic conductors number 4. The resistance shown by an electrolyte solution is due to the factor like interionic attraction, viscosity of solvent, etc. Electrolytic resistance and conductance. Every substance offers resistance to the flow of electricity to a small or large extent. The law that gives the exact value of resistance is known as Ohm's law. It states that if to the end of a conductor a voltage E is applied and current I flow through it, then the resistance R of the conductor is E by I. Current is generally measured in ampere, whereas voltage is measured in volt. If 1 ampere current flows through a conductor when a voltage of 1 volt is applied to it, the resistance of the conductor is taken as 1 ohm. According to Ohm's law, R is equals to E by I. Ohms is equals to volt per ampere. SI unit of ohm is kg meter square per second cube ampere square. It is obvious that a substance which offers greater resistance will allow less electricity to flow through it. This result also follows from Ohm's law, according to which I is directly proportional to 1 by R. The reciprocal of the electrical resistance is called the conductance. It is usually represented by C. Thus, C is equals to I by R. It is a common practice to speak conductance of a solution rather than its resistance unit. The unit of conductance are Simon or reciprocal ohms, written as per ohm or mho or per Simon. Specific conductance or specific conductivity, simply called conductivity. Number 1. Directly proportional to its length of the conductor. Number 2. Inversely proportional to its area of cross section. R is directly proportional to L by A. R is equals to rho L by A, where rho is a constant of proportionality. Specific resistance or resistivity, its value depend upon the material of the conductor. The reciprocal of resistivity is known as specific conductivity, or simply conductivity is denoted by kappa. Kappa is the specific conductivity and C is the conductance of the solution. Then R is equals to I by C, 1 by C, and rho is equals to 1 by K. So K is equals to C cross alpha L by E. Specific conductance or specific conductivity, or simply called conductivity of a solution, is defined as the conductance of a solution of 1 cm length and having 1 square centimeter as the area of cross section. Alternatively, it may be defined as conductance of 1 cm cube of the solution of electrolyte, or in terms of SI base unit, it is defined as the conductance of 1 meter cube of the conductor. If the volume of solution is V centimeter cube, the specific conductance of such a solution at the dilution V is written as Kv. Similarly, at concentration C, it is represented by Kc. Unit specific conductivity K is equals to 1 by rho. Equivalent conductance or equivalent conductivity. Equivalent conductance of a solution at a dilution V is defined as the conductance of all the ions produced from 1 gram equivalent of the electrolyte dissolved in V centimeter cube of the solution when the distance between the electrodes is 1 centimeter and the area of the electrode is so large that whole of the solution is contained between them. It is represented by lambda. Relationship between equivalent conductance and specific conductance. The equivalent conductance of a solution is usually not found directly but is calculated from the specific conductance. The relationship between equivalent conductance and specific conductance may be obtained. Molar conductance or molar conductivity. The molar conductance of a solution is defined in a manner similar to that of the equivalent conductance is as under. The molar conductance of a solution at a dilution V is the conductance of all the ions produced from 1 mole of the electrolytes dissolved in V centimeter cube of the solution when the electrodes are 1 centimeter apart and the area of the electrodes is so large that the whole of the solution is contained between them. It is usually represented by lambda m. Relationship between molar conductance and specific conductance. Lambda m is equals to Kv cross V. Lambda m is equals to Kc cross 1000 by C is equals to lambda C cross 1000 by molarity, where K is the specific conductance and V is the volume of the solution containing 1 mole of the electrolytic and C is the molar concentration, that is mole per liter. Variation of conductance, specific conductance, equivalent conductance, and molar conductance with dilution. In general, electrolytic conductance as well as equivalent conductance and molar conductance increase with dilution, whereas the specific conductance of an electrolytic solution decrease with dilution. The reason for that is the conductance of a solution is due to the presence of ions in the solution. The greater the number of ions, the greater is the conductance. As on dilution, more ions are produced in solution, so the conductance should also increase on dilution. The specific conductance of an electrolyte falls with dilution because the total number of current carrying particle, that is ions, increase with dilution, but ions present per centimeter cube of the solution becomes less and less on dilution. However, the increase of equivalent and molar conductance on dilution is due to the fact that these are the product of specific conductance and the volume V of the solution containing 1 gram equivalent or 1 mole of the electrolyte. As the decreasing value of specific conductance is more than compensated by the increasing value of V, so the value of lambda equivalent and lambda m increase with dilution. Variation of molar conductance with concentration. As already mentioned in the beginning of the chapter, there are two types of electrolyte, namely strong electrolyte and weak electrolyte. The variation of molar conductance with concentration for each of these electrolyte is briefly discussed below. Conductance behavior of strong electrolyte, as discussed later in more details. The molar conductance of strong electrolyte is found to vary with concentration according to the equation lambda mc is equals to lambda m naught minus b under root c, where b is a constant depending upon the type of electrolyte, the nature of solvent, and the temperature, and lambda m is the molar conductance at infinite dilution, called limiting molar conductance. This equation is called Debye-Huckel-Onsager equation and is found to hold good at low concentration. Thus, if lambda mc is plotted against under root c, a linear graph is obtained for low concentration, but it is not linear for higher concentration, as shown, in which KCl has been taken as an example of strong electrolyte. Further, the curve obtained for a strong electrolyte shows that there is a small increase in conductance with dilution. This is because a strong electrolyte is completely dissociated in solution, and so the number of ions remain constant. At higher concentration, the greater interionic attraction retarded the motion of ions, and therefore the conductance fall with increasing concentration. With the decreasing in concentration with the dilution, the ions so are far apart, and therefore the interionic attraction decreases, due to which the conductance increases with dilution and approaches a maximum limiting value at infinite dilution, designated as lambda m or lambda m infinity, lambda m naught. Conductance behavior of weak electrolyte. As a weak electrolyte dissociates to a much lesser extent of compared to a strong electrolyte, therefore the conductance of weak electrolyte is much lower than that of a strong electrolyte at the same concentration. This is in which acetic acid has been taken as example of weak electrolyte. Further, the curve obtained for a weak electrolyte shows that there is a very large increase in conductance with dilution, especially near infinite dilution. This is because the concentration of the weak electrolyte is reduced, more of it ionized. Thus, increase in conductance with decrease in concentration is due to the increase in the number of ions in the solution. However, it does not reach a limiting value. Postulate of Arrhenius theory. To explain a number of phenomena related to electrolytics such as conductance, electrolysis, anomalous behavior of electrolyte towards colligative properties, Arrhenius put forward a theory about the electrolytes. This theory is known as Arrhenius theory of electrolytic dissociation. The main point is number 1. An electrolyte when dissolved in water splits or dissociate into positively and negatively charged particle called ions. The process is called ionization, or more correctly electrolytic dissociation. Example, NaCl coating Na positive, Cl negative. The total charge carried by the positive ions is equal to that carried by the negative ions, so that the solution as a whole is electrically neutral. On number 3, on electrolysis, the positive ions migrate towards cathode and hence are called cations, while the negative ions migrate towards the anode and hence are called anions. Number 4, and the ions formed constantly reunite to form the undissociated molecule till ultimately there is an equilibrium between the ions and the undissociated molecule. In other words, the whole of the electrolyte may dissociate into ions. Instead, only a part of electrolyte may dissociate into ions. The fraction of the total number of molecule or of the electrolytic dissociate into ions is called degree of dissociation. Degree of dissociation is equal to number of molecule dissociated upon total number of molecule taken. Number 5, the degree of dissociation increase with dilution and decrease become maximum at infinite dilution. Number 6, the conductance of an electrolytic solution is due to the ions produced by the dissociation of the electrolyte. Greater the dissociation, the higher is the conductance. Substance like mineral acid, alkalis, and most of the salt which show at higher conductance is due to the fact that they possess high degree of dissociation, that is therefore their molecules are almost completely dissociated into the ions aqueous solution. Such substances are called strong electrolyte. On the other hand, substances like organic acid bases, inorganic acid, and inorganic bases which show poor conductance is due to the fact that they possess low degree of dissociation, that is they are only partly dissociated in aqueous solution. Such substances are called weak electrolyte. Number 7, the ion produced by the dissociation of an electrolyte behave like molecule towards colligative property. For example, each NaCl molecule dissociated to give two ions, Na positive and other is Cl negative. Hence, the observed value of any colligative property is double than the expected value. Number 8, the properties of an electrolyte and are the properties of its ions. For example, the properties of an acid are due to the H positive ions furnished by it in the aqueous solution. Similarly, the properties of base are due to the OH negative ions produced in the aqueous solution. Ostwald dilution law. According to the Arrhenius theory of ionization, when an electrolyte is dissolved in water, there is an equilibrium between the ions and the undissociated molecule. For example, a binary electrolyte AB equal to A positive, B negative. Ostwald pointed out that the law of chemical equilibrium can be applied in the ionic equilibrium. As a result, he obtained an important relationship known as Ostwald dilution law. Suppose the initial concentration of binary electrolyte AB in the solution is C mole per liter and alpha is the degree of dissociation, then we will have initial concentration AB C mole per liter, A positive 0, B negative 0. Concentration at equilibrium AB C minus C alpha, A positive C alpha, B negative B C alpha. Applying the law of chemical equilibrium, K is equals to C alpha square upon 1 minus alpha. The equilibrium constant K for the equilibrium AB, A positive plus B negative, is called dissociation constant or ionization constant of the electrolyte AB and may be represented by Kd. Like any other equilibrium constant, Kd is constant only at constant temperature. The unit of Kd will be same as those of the concentration C. If the degree of dissociation is alpha is very small, as is usually the case for weak electrolyte at ordinary concentration, alpha can be neglected in comparison to 1 in the denominator of expression. Then the approximate formula becomes Kd is equals to C alpha square or alpha is equals to K under root Kd upon C. For a weak binary electrolyte with a small degree of dissociation, the degree of dissociation is inversely proportional to the square root of the initial molar concentration. Kd is equals to alpha square upon 1 minus alpha into V, where V is the volume for the solution in liter containing 1 mole of the solute. Thus, Ostwald dilution law may be defined. For transport number, when an electric current is passed, the ions migrate towards the electrodes. Thus, the electric current is carried by ions. Each ion carried a definitely fraction of the total current depending upon its speed. The fraction of the total current carried by an ion is called transport number or transference number or Hitrov's method number. Greater the speed of ion, greater the amount of current it will carry with it, and hence greater will be its transport number. Let UA and UC be the speed of anion and the cation respectively. Current carried by the anion directly proportional UA is equals to K dot UA. Current carried by the cation directly proportional to UC is equals to K dot UC. Since current is carried only by ions, that is total current carried is equals to current carried by anion plus current carried by cation is equals to K dot UA plus K dot UC is equals to K into UA plus UC. Transport number of anion Na is equals to K UA upon K into UA plus UC. Na is equals to UA U upon UA plus UC. Similarly, transport number of cation will be NC is equals to UC upon UA plus UC. Two important relation Na plus Nc is equals to UA upon UA plus UC upon UA plus UC is equals to UA plus UC upon UA plus UC is equals to 1, or Na plus Nc is equals to 1. That is, the sum of transport number of anion and cation of electrolyte is always unity. Thus, no current is lost in any other function and the whole of the current is carried by the ions. Second, Na is equals to UA upon UA plus UC is equals to 1 upon 1 plus R, where R is equals to UC upon UA, speed ratio of cation of the anion. Na is equals to UA upon UA plus UC is equals to 1 upon 1 plus R. Nc is equals to UC upon UA plus UC is equals to R upon 1 plus R. Determination of transport number. There are a number of methods for the determination of transport number. Example number 1, Hitrov's method. Number 2, Lowell's moving boundary method, EMF method, etc. Hitrov's method. Principle. The method is based upon the principle that the fall in concentration around an electrode is proportional to the speed of the ion moving away from it. Fall in concentration around cathode upon fall in concentration around anode is equals to U upon UC. 1 plus fall in concentration around cathode upon fall in concentration around anode is equals to U upon UC plus 1. Fall in concentration around anode plus fall in concentration around cathode upon fall in concentration around anode is equals to UA plus UC upon UC. Total fall in concentration around both the electrode upon fall in concentration around anode is equals to UA plus UC upon UC. Fall in concentration around anode upon total fall in concentration around both the electrodes is equals to UC upon UA plus UC is equals to NC. If the concentration are expressed in terms of gram equivalent, both for the above expression may be written as NC is equals to number of gram equivalent lost from the anodic compartment upon number of gram equivalent lost from both the compartment. It may be seen that the number of gram equivalent lost from both the compartment is equal to the number of gram equivalent discharged on each electrode. This can be found by placing a silver or a copper voltmeter in series, as according to Faraday's second law, where the same quantity of electricity flows through the silver or copper voltmeter, the same number of gram equivalent of the Ag or Cu will be deposited. Nc is equals to number of gram equivalent lost from anodic compartment upon number of gram equivalent deposit in voltmeter. Thus, the determination of transport number of cation involves determination of number of gram equivalent of lost from the anodic compartment and number of gram equivalent of Ag or Cu deposited in the voltmeter placed in series with the apparatus. However, it is important to note that the above result is applicable only when the electrodes are not attacked by the ions. If the electrodes are attacked, the result is calculated in a different manner, as discussed. Procedure. Number 1. The apparatus is filled with the solution of the electrolyte, the transport number of whose ions is to be determined. Number 2. A silver of copper voltmeter is placed in series with the apparatus and the various connection made. Number 3. Before electrolysis, the concentration of the electrolyte is found by titrating a known weight of the solution against a suitable reagent, against KSCN solution for AgNO3 solution and against hypo solution of CuSO4 solution. Number 4. Now a current of 0.01 and 0.02 ampere is passed for 2-3 hours. A low current is used so that the change in concentration around the electrodes is not too high, as otherwise the diffusion may take place. Number 5. After electrolysis, the solution from the anodic compartment is taken out, weighed and then titrated as before to know the amount of electrolyte present. Number 6. The weight of the silver deposited in the silver voltmeter or that of the copper in case of copper voltmeter is used is also determined. Number 7. The solution from the central compartment is also taken out and titrated to see that there is no change in concentration within the experimental errors. In case a change in concentration is observed, the experiment is repeated. It is important to note that in these measurements, the weight of the solution are taken instead of volumes. This is necessary because after electrolysis, the density of the solution changes and so does the volume. So here completed electrochemistry part 1. Thank you.